here we go. It's actually quite funny. I'm guessing the people sitting at the bar behind the computer are having a good laugh because they can see my presentation notes and they know that I'm reminding myself to introduce me because I don't know how many times I've come up here on the stage to talk to all you folks and never actually say, hi, I'm Tyler. But yes, hello, I'm Tyler at Astronomy if you want to follow me on Twitter. I don't tweet, but it's there if you want to. And I'm a grad student at Louisiana State. I work with Tyler Ellis, my very first AOT speaker, and we do some cool stuff that's completely unrelated to what I'm speaking about tonight. So fingers crossed the clicker works, and here we go. So the talk tonight is that burning feeling, and at the end of the talk, when I was finished making my slides, I was like, yeah, maybe not the best thing, but it's all about being burned by the sun, just not, cooked by the sun. So before we invoke the ire of the sun, let's talk about all the things we like about the sun. I know we get a lot of it down here in Baton Rouge, and this last week has been quite the challenge. But, the sun does some good stuff. We all like leaves. We all like kale, right? It's good for you. And we like having vitamin D, calcium regulation. It helps with depression. It helps with liver and kidney function. I like having those, especially on Astro Attack. Having a liver is good. And rainbows, rainbows are cool. So, without further ado, let's invoke the ire of the sun. So, this is the sun. It's big, round, it's hot. But more correctly, let's ask the might be giants what the sun is. Yes, you heard it right. The sun is a massive incandescent gas, a gigantic nuclear furnace. So we need a slightly more complicated understanding of the sun for this talk to really mean a whole lot. So inside the sun, it's just a big ball of gas composed of hydrogen, helium, everything on the periodic table. And at the very core, we have gravity compressing this gas down to crazy high temperatures, millions of degrees. Pick your unit, it's correct. And we're smashing protons into protons, and here we get the chain going. So we have proton to proton making deuterium, which is heavy hydrogen. You put some deuterium together and you get a light helium particle, and you put some light helium particles together and you get a nice proper heavy helium and some protons back out. And that all happens in the core. And along the way you saw it made some extra things. It made neutrinos, it made photons, and that stuff wants to go out. The neutrinos, they can cheat. They can just zippy zoom right out through the mass of the star, and within 8.5 minutes we're here on Earth getting all those neutrinos right through our body, trillions of them every single day. But the photons, they have to go through the radiation zone. So here's a lovely little animation I bleeped together in a little bit of time. So every photon, it picks a direction and it takes a step forward, and then it hits something. It'll hit a bit of gas, or it'll scatter off an atom, and it then goes off in another random direction, and it bounces back and forth and up and down and whatever, but it's not necessarily moving out of the sun. So all along the way, it's taking these baby steps, what's called a random walk. And what happens is, the light that's created at the core of the sun doesn't get out, and it doesn't get to the Earth in the 8.5 light minutes it takes to, or the 8.5 minutes it does take to travel. Instead, it takes something on the order of 250,000 years for it to go from the very core of the star to the exterior. So the next part of the sun is the convective zone. And here's a lava lamp, in case you've never seen one before, and that's exactly what it's doing. It's boiling. So the fusion of the core is heating up the gas, and it's becoming less dense, and then it goes to the top, and then it cools off, and then it goes back down, and it's just a big pot of boiling water. But if you put your spaghetti in there, you wouldn't have dinner. You would die. So now that we sort of understand the inside of the star, let's take a look at the outside of the star. So when we're looking at the sun, as we were told not to, we can see a couple things. So looking, whoops, wrong button, there we go. So this is the sun as it was just a few days ago, and you can see we've got these little spots here, and you can see some granulation, and that's what they were called, they're the granules. Each of these little spots on the star is about the size of Texas, and then the really, really big spots, like these guys, those are about the size of Earth. So we had Kelsey talking last month, And I hope she left you guys with a nice impression of exactly how big the sun is. So you can fit so many Earths inside, millions, and it's just stupidly massive. But again, the things to take away is each of these little granules, Texas, each of the big spots, the Earth. So we're looking at what's called the photosphere and the chromosphere. So this is the atmosphere of the sun. And there's one thing that you can't see here, and that's the corona. And the corona is the most exterior atmosphere of the sun. It's extending far above what you would consider the surface. And the really confusing thing is, so we started at millions of degrees inside the star, and we slowly got cooler as we went up, and then on the surface, we're sitting at a nice balmy 6,000 Kelvin. So, you know, weather last week. And then, confusingly, once you've left the surface, you get hotter. So something weird is happening in the magnetic fields, and it's causing the plasma to be heated up, and it's actually on the order of millions of degrees. And that's one of the big mysteries in astrophysics at the moment. So we have the inside of the star, and we have the outside. And we observe this in a variety of ways. So we use ground-based observatories, such as the 150-foot solar tower on Mount Wilson. And with that, we can do daily monitoring of the sunspots, and we can try and make measurements of the magnetic field. But some of the images that you see here, they're different colors, and they're false color images because that's just the best way we choose to represent colors of light we don't see with our eyes. So those greens and those blues and purples, those are probably stand-ins for colors such as ultraviolet light or even X-ray. And to observe the sun in UV or X-ray, you have to actually go up above the atmosphere of the Earth. Earth's atmosphere is amazing and protective, and if we didn't have it, much like if we didn't have the sun, we would be dead. But what the atmosphere is doing is it's absorbing those UV and the X-rays and making it impossible to observe the star in those colors of light. So we also have space-based observatories. So probably the most commonly known one would be SOHO, the Solar Heliospheric Observatory. But these have all just been standard, simple pictures, not moving. But we can't forget that the sun is a living, breathing organism. And ignoring the fact that the screen's wibbling, you can see that matter's poking up and out, and the sun is rotating. And this is all over the course of many hours, many days. So this is where things get complicated. There are a couple things that make astronomers shake in their boots, and I think the one that most people would agree with is magnetic fields. That boiling of the plasma underneath the surface and the complicated rotations that you saw in the previous slide, this is doing terrible, terrible things to the magnetic field. You might like your fridge magnets, you might like your bar magnet, who knows, maybe you like the electromagnetic thing in your hard drive, but once you're generating magnetic fields with boiling plasma and you have it rotating, the magnetic fields are so complicated we can't just simply draw lines from north to south. So we have someone much more qualified to say things about the magnetic field of the sun. So let's hear what they have to say.
The sun is a beautifully magnetically driven star, but we can't actually see magnetic field lines. They're essentially invisible, and so we have to turn to models in order for us to see the global magnetic structure of the sun.
So all of those lines connecting things on the sun, those are the magnetic field lines of the sun. It's not a simple north to south thing. You've got north to south just going slightly across the surface of the star. You've got north to south going from the top to bottom of the star. It's beyond complicated, and trying to actually say what's going on there is not a simple process. But I promised you death by the sun. I've talked about the structure of the sun, I've talked about magnetic fields, and I've talked about lava lamps, but I haven't talked about how the sun's going to kill us yet, and I'm getting to it, I promise. So this is the most fantastic picture I've seen in a good long while. It is a composite, so it is slightly Photoshop. It's a combination of slightly different wavelengths put together, but this is a beautiful, beautiful picture of a solar prominence. So when those magnetic fields poke up off the surface of the sun, the charged gas that is the surface of the sun can follow along those field lines and poke out of the surface. And sometimes those field lines break. And what happens is that matter gets flung off into space. You might know the product of that occurrence as the northern or southern lights, or the aurora. So here's some beautiful footage of the aurora from the International Space Station. So here we have it just tracking over the Earth, and as that charged gas from the surface of the sun flies across the solar system and it hits the Earth, it goes into the Earth's magnetic field, which is much, much better to model, but still complicated. And it goes into our atmosphere, following along those field lines. And this charged gas, it has enough energy, and it has the capability of ionizing the gas in our atmosphere. And when you ionize gas and it recombines with new electrons, you get light coming in and out. And this is what produces the aurora. So it's most prominent at the poles, because that's where the magnetic field lines are then poking back into Earth. But it's all quite pretty. But what happens when you get a lot of gas from the sun? So really the event that inspired this whole talk was the 1859 solar storm, or as some of you might better know it as, the Carrington Event. So in 1859, a large coronal mass ejection happened. That's the big fancy word saying coronal mass. So some mass from the star exited via the corona. And that's it. We just have to use complicated words to validate our paychecks. And what happened is there was so much plasma that went through the space and encountered Earth that, so we didn't have phone lines at the time, but we did have telegraph lines. When that plasma entered the atmosphere, it induced enough electricity in these telegraph lines to be operated without their battery. Now, I showed, let me actually explain this image. This is a similar style event to the Carrington event that happened in 2012. Fortunately, it was not pointed at Earth at the time, so the plasma went harmlessly out into space and we all survived nice and fine. But what happens when that actually does come in contact with us in the modern world? And even worse, what happens when you get an event that's many magnitudes stronger? So here is a terrifyingly strong coronal mass ejection happening in 2001. This is the largest observed coronal mass ejection. And you can see that the amount of mass ejected overloaded the instruments that were observing it. That's what those streaks are. The camera can't handle how much matter it's interacting with. So here's what happens. Like I said, that plasma flies through space, encounters our Earth's atmosphere, and starts to spiral along the magnetic field lines. Lenz's law, some other electromagnetic stuff, and what you have is an induced electrical current that's happening in the loops of wire that we've crisscrossed across Earth, known as our power grid. Now, our power grid is robust, and it can handle some variation in the current, but we like to have it at our high voltage and frequency stuff to beam across the ground. But when it goes bad, this happens. I love the people who upload stupid videos to YouTube. So this is a protective relay. So when there is an abnormal current registered in the network, the little dial at the top, let me hit the right button this time, starts to spin, and this contact here moves over to these plugs and breaks a circuit. And that's good. It means that the power grid is protected and that we don't have our transformers doing this. This is bad. I'm sure we've all encountered one of these exploding in our nearby neighborhood at some point in our life, and we all get really upset. We've lost power for a couple hours, maybe a day. But what happens if that X20 solar class flare hits the Earth? Suddenly, all of the transformers on Earth have tripped, and it's going to take a lot more than just a few hours to get it fixed. It's going to take a lot more than a few days to get it fixed. And this is a problem. So what do we do? At that point, we've lost all of our satellites. Our satellites are fried. They don't even have the slight protection of the atmosphere. They don't even have the slight protection of the magnetic field. They're gone. So every single satellite activity you do is gone. You don't have GPS anymore. You've lost your ability to do financial transactions if you use credit cards. We've lost our internet. We've lost power. What do you do? Well, you wake up and you see your alarm clock's dead. You go outside and it's oddly quiet. You go to work, work's locked. The doors don't open. You go to the grocery store, the doors have been pried open. People have already broken in and stolen the food. But what can we do to protect ourselves from this future? Well, I don't know. I'm sorry, there's no good answer. We can tell the power companies that they should prepare for an event like this, but that's expensive. They've got to have more transformers sitting around ready to go for an event that might not even happen. An astronomer calculated the probability of a Carrington-style event happening in the next 20 years at 17%. That's not a lot, but that's 20 years, 17%. It's more than I'd like to risk. So I hope you've taken away from this that the sun will one day destroy us all. But here's another way it might destroy us. I hope that cheered you up a little bit. All right, so thank you so much, guys, for your patience. Solar flares, man, they're very real. They happen all the time. And if they decide to come and hit us, there's not much we can do about it. So write to your politicians, write to your power grid, tell them to make more transformers. And with that, I welcome your questions. Thank you so much. Actually, that's a really fun question. So she asked, do we have equipment that gets super close to the sun and how we measure it? So there are things that the sun can do that are indicative of its magnetic field, of its temperature. We can even measure seismic waves moving through the sun by measuring disturbances in... So I'd have to explain spectroscopy. By keeping an eye on the fingerprints of elements in the sun, we can see how they're moving, and that can tell us about the motion of the sun overall. But one very topical thing in regards to going close to the sun and doing experiments would be the Parker space probe. So we recently launched a satellite whose sole purpose is to go nice and close to the sun and to go into the corona to pick up the matter there and see what is it made out of, what's going on with it, what's the magnetic field over there like, because we want to solve that coronal heating problem. We want to figure out why the corona is as hot as it is. I hope that... Define close. I actually don't know that exact answer. I'm sorry. About that. Hopefully more than an inch.
So on that video you had of the X20 event, there was a ton of photon hits before the actual reunion. Does that mean that there was some sort of buildup to it where they predicted it happening, or was it just sort of the event already had started occurring even though we hadn't had that explosion?
So the question was, why was there already some streakiness on the spectrograms of the sun before the X20 class flare actually went off? So as was the case with the 2011 solar storm video I had, these storms sometimes happen in a streak. So you'll have one little baby flare and then another one will come along. So it's possible that at that time there was already an ejection that had happened and had been overloading the camera before the big X20 did. Yes, please.
All right, so in certain things, I know that a lot of people that do ham radio, a lot of them will wrap their radios with foil, but are other organizations actually preparing accordingly, that you may have heard of already for things like this?
That is a great question, whether or not people are getting prepared for this style of event. Yeah. So another similar event was in 1989. Quebec Hydro lost the power to the whole Quebec region. For 9 hours, there was no power, no trading, no commerce, no nothing. And that was a big issue. Like, there was a massive financial loss because of that. And I believe that in response to that, they are now more prepared. That would be one case. But actually, I can't say for certain whether or not there are big organizations getting ready for an event like this. But I would like to explain why people wrap their ham radios in tin foil. That's to construct what's called a Faraday cage. So there's another fun physics things for you. Just as the telegraph lines, when they get the charge current, it's the induced current, the goal is to electrically isolate the device from any outside current. So you can do this at home if you're in the mood for some weird science. Just take a sheet of aluminum foil and a metal colander and put your phone on the inside, and your phone will lose all of its service. It won't be able to connect to Wi-Fi or the cell network, and that's because the current is being induced in the colander and the tinfoil rather than inside your phone. Yes, please.
So how far would you say that the plasma ejections go out into the solar system? Would it affect people on Mars, for example?
That's actually one of the big problems. So the question is, how far out does the solar corona ejections actually go? And they go out and beyond the reach of the sun. So there's a region called the heliopause, which is the official end of the solar system. So it goes all the way out there. And actually, one of the big problems we need to overcome if we want to do spaceflight is how do we protect astronauts, or to be Marsnauts, who knows, not only on the transit to Mars or wherever, but once they're on there. Because once they're outside of Earth's magnetic field, they're losing a lot of the protection that Earth offers us from these harmful particles. So these charged particles, they're protons, they're neutrons, they're electrons. They have the ability to ionize our DNA, which is bad, and that's cancer, and that's death. Yes, please.
So part of Earth is usually pretty good at blocking electromagnetic radiation. Is there a reasonable depth that we can maybe bury cables under in order to protect them from something like a coronal mass ejection? Or is there any other kind of reasonable measure we can go to prevent this?
So the question is, what measures can we take to protect our electrical equipment from a solar flare event? So those relays, just as bad as they were, that's what caused the New York blackout. A faulty relay tripped and disconnected the electricity to all of New York City, and that was a bad thing. But good functioning relays, when they're in place and properly functioning, that will divert the charge current away from the transformers and protect the network. The other things we can do, you suggested burying. Unfortunately, cosmic particles like that, they're really good at getting in and past. So if there's actually a large enough flux of the coronal mass ejection, it will deform the magnetic field, and then the matter can get further and deeper down. So a big event like that does have the possibility of causing a lot more problems, even if we do take appropriate measures. Yes, please.
So the solar probe that's been launched, does it have to have special shields or possible as it gets close to the sun?
I would. So the question was, did the Parker probe have special protections from the nearby atmosphere of the sun? I am not actually super familiar with this probe, other than just the general mission of get close to the solar corona and study it. Any of the astronomers in the audience have a good answer to that?
Watch
The video?
carbon and carbon foam and more carbon. It's about that thick,
Ah.
and it faces the sun.
Oh, so
There's also a water system that helps take the heat away.
okay, so he was saying there's like a bunch of insulating material to protect it from the heat. That would be one of the big risks. You half your distance to the sun, and you've what's the word? Quartetted 4 times? Quadrupled. Ha! Latin! Yes, you've quadrupled the amount of energy you're absorbing. As for what's protecting it from the charged particle, the solar wind, I don't have an answer for that.
I'll take one more question.
Yes, please.
Can we predict flares within what time frame?
So that's a really fun question. Can we predict flares, and within what time frame? We do know that the sunspots are connected to flares, and periods of time when there are more sunspots, you have a greater likelihood of a big flare happening. So to that extent, there is a period, a magnetic cycle period with the sun. So every 11 years, we go from a solar maximum to a solar minimum in the number of sunspots that we're seeing. We're currently just coming out of a minimum, right? Seems about right.
I think so.
Yeah. So if we know that there's more sunspots, we can sort of preemptively prepare. We can say, okay, there's a better than average chance that we're going to have a big flare, but we can't predict when those magnetic field lines will break super well.
So I'm going to talk about black holes, and as you can see, and thanks to Tyler for coming up with a catchy title. I'm not very good at that, so but of course now I have to explain why black holes are magic, but I hope I will convince you about that before the talk is over. So let's just get going. Yeah, it works. So first, the basic foundation for talking about black holes is Einstein's general theory of relativity. Before that, we had Newton's theory of gravity. And I just want to say a few things about the difference between those, because it's kind of important to understand. So in Newtonian gravity, physics unfolds on what we call absolute space and time. So yeah, there's an absolute space that doesn't change, and there's an absolute time that ticks at the same rate everywhere in that space. And on that background space, gravity was seen as an instantaneous force between every massive objects in the universe. And this worked really well since it was formulated. It was very good at describing the motion of the solar system, the planets and moons around the planets. Except that there was a little thing where Mercury didn't really behave the way it was supposed to. And then in 1915, Einstein came along with his general theory of relativity. And this is a completely different view of gravity. So in his theory, physics unfolds on a dynamic four-dimensional space-time. So it's a four-dimensional objects, three-dimensional, three space dimensions and one time dimensions, and they are all connected and all react to what is going on in the universe. And here, gravity is nothing but curvature of space-time itself. And so the way it works is that massive objects and anything in the universe with energy or mass curve space around it. So matter tells space-time how to curve. And then the curved space-time tells matter how to move. So this is a very different view. And for example, you're sitting here and you think about you sitting still, you're not being accelerated. But in Einstein's theory of general relativity, the natural motion of a body is free fall. And so in Newtonian theory, you would be feeling that you're not accelerated because the Earth is providing a force that counteracts the gravitational force. But in Einstein's theory, you are actually accelerated, or because the Earth pushes up on you and stops you from falling freely. And so it's a very different way of thinking about gravity. So one thing is also that the difference between those two viewpoints only really comes out in a strong way when gravity is really strong. And you have to do really accurate measurements in order to detect these effects for the kind of strengths of gravity we have here on Earth. So Einstein's theory was published in 1915, and already the same year, but published the next year, Karl Schwarzschild came up with an analytic solution to the Einstein equations, or Einstein's field equations, that describes the space-time around a spherically symmetric object. And the curious thing was that if you let the object shrink down to a radius that is smaller than this radius that I've written up here, the Schwarzschild, what is currently known as the Schwarzschild radius, it turns out that the solution has seemed to have a singularity at that radius. We now know that this is not a real singularity, but just an indication that this was actually describing a black hole. Of course, this was realized really quickly, but most people wouldn't actually think that any astrophysical object could actually be close to this limit, so didn't really pay attention to this for many years. And the term black hole was actually first used by John Archibald Wheeler in 1968. I have to look at the year there. And before that, people were calling these objects dark stars or frozen stars. But the black hole description is actually quite apt. So let's go on and actually talk about what is a black hole. And so a black hole is defined as a region of space-time from which light cannot escape. And the boundary of that region is called the event horizon. And so Tyler was just talking about the sun, and last week there was a talk about how big the sun is. In order to make the sun into a black hole, you have to compress all the mass that is in the sun to a radius of 3 kilometers. So that's why we talk about compact objects when we talk about black holes. And so what are some of the magical properties? And here, now we're talking about magical properties, and that is that a black hole essentially can slow down and in some sense stop time. So if we have an observer, let's call her Alice, that sits far away in safety, lowers a clock, she has a very strong string, down towards the black hole, and she observes the clock. Every second the clock emits a pulse of light that she can observe. She finds that the clock slows down, and it slows down more and more as it approaches the horizon. But in addition to that, also, so for example, you could say, okay, the clock emits a blue laser pulse every second, but this light has to climb out of the gravitational well of the black hole, and in doing that, it gets redshift, as we call it. The frequency of the light changes as it moves out. And so in a certain position, it will turn into red light, and then it will turn into infrared and radio waves. And if you actually were to lower the clock all the way to the horizon, it would go to essentially infinite wavelength. So she wouldn't actually be able to observe the clock as it goes down towards black hole, because the light would be redshifted. Now we have another observer, Bob. He's a little bit more daring, so he decides to, okay, let me free fall towards the black hole and see what happens. And he has a little flashlight, and he sends out light that Alice can observe. And again, from Alice's viewpoint, as he falls towards the black hole, he slows down, and the time between his flashlight pulses becomes longer and longer. And also, we have the same redshift effect as well. But if Bob looks at his clock, and as he moves towards the horizon or the black hole, he doesn't see anything special. The clock still ticks at the same rate. And actually, according to his time, he will actually reach the event horizon in a finite time. And if the black hole is big enough, and in this particular case, it would have to be more than 1,000 times the mass of the sun, Bob would not even realize anything special happening at the horizon. But as he goes into the black hole, he will actually find that there's no way that he can, with any rocket, that he would be able to come back out again. And even his light pulses that he sends out towards Alice actually, even if he sends it out radially outwards, will actually go towards the center of the black hole as well. And as he gets closer and closer to the center of the black hole, where there's actually a real singularity, he will experience stronger and stronger tidal forces. Essentially, the gravitational field is stronger near his feet than his head, so the effect is they get stretched. And also, he gets compressed in the other direction, so around his waist. And so, essentially, what happens is he gets spaghettified, as we call it. So he gets stretched into a long piece of spaghetti, and eventually he gets pulled apart. And then, of course, all the pieces of Bob will then fall in and hit the singularity in finite time. So that's death by a black hole. Is you get pulled apart, and then you get crushed by the singularity. But Alice will never be able to see his death in there. She can't see that. And then also, but if the black hole is it's much less than 1,000 solar masses, Bob will actually be ripped apart before he even gets into the event horizon. So if you actually want to go inside the black hole, you actually have to find one that is big enough that you can actually survive the trip. Another curious fact is that if he actually sends out light in the horizontal direction at a radius of 1.5 times the Schwarzschild radius, light can actually go in circle orbits around the black hole. So you could actually, if you were sitting there, if you had a strong enough rocket, you could actually emit light and then come back and hit you in the back of your head. So another curious thing about black holes is that they're very simple objects. They're described by very few parameters. The Schwarzschild solution that describes a spherically symmetric black hole only has one parameter, and that's the mass. In 1963, almost 50 years after the equations was formulated, Roy Kerr found another solution, another analytic solution to the equation describing a rotating black hole. And that solution has two parameters, the mass and a measure of the rotation that we call angular momentum. In principle, you can also put electrical charge on a black hole. We don't expect that to happen astrophysically. There was a solution found by Ted Newman in 1965. But we don't expect black holes to have any significant charge, because if you were to make a black hole negatively charged, it would attract positive charges and discharge that way. In contrast, normal stars, you need many more parameters to describe them. Besides mass rotation, you have rotation profile, you have chemical composition, you have the age, and so on, in order to describe a normal star. So black holes are really, really simple objects. And they can be summarized in the statement that black holes have no hair. We forget everything about what falls into the black hole. You can build up a black hole by peanut butter or by something else, and the space-time outside will still be the same. So the question is, do black holes really exist? And until 2015, we only had indirect evidence. Some of the evidence we had was stuff called X-ray binaries, where you have a black hole or neutron star, but in some systems we can actually determine that it's a black hole and not a neutron star, with a normal star around it. And the normal star deposits mass onto the black hole, but it has to go through what we call an accretion disk in order to get rid of the rotation of the material. And the famous example is called Cygnus X1, one of the first X-ray sources in the sky that was observed. Also, active galactic nuclei in galaxies and quasars have a supermassive black hole of between 10 to the 5 to 10 to the 10 solar masses, and an accretion disk around it that emits a lot of energy. And then we also had a few what we call extreme luminosity X-ray binaries that hinted at there being black holes with masses between 100 solar masses and 10 to the 5 solar masses. But this was all, I mean, it was not direct evidence of the black holes. but it's very likely, still we found that it was very likely that almost all galaxies had a black hole at the center. Even our own galaxy, our own Milky Way, has a black hole of about 4 million solar masses at the center. So before talking about what happened in 2015, I have to tell you a little bit about something called gravitational waves. And that's a prediction from general relativity that predicts that accelerated masses will emit gravitational waves. And the larger the masses and velocities involved, the larger the gravitational waves will be. And so in order to get really strong fields, you have to have heavy masses moving really fast. And the most efficient way you can do that is by having compact objects, because then they can get really close together and feel really strong gravitational fields and move really fast. And so gravitational waves essentially are ripples in space-time that propagate out from the source. And they, according to theory, are traveling at the same speed as light. And so the effects that they have on a ring, if you imagine a ring of freely falling test masses or freely moving test masses that are oriented in a circle, is that if the gravitational wave comes in from this direction, that it will stretch this ring in one direction and compress it in another direction. Then it will go back to circular shape, and then it will be stretched and compressed in the orthogonal directions to this one and go back, so as a wave passes through. And we now have gravitational wave detectors like LIGO and Virgo that can detect these astrophysical systems. And this is what happened on September 14, 2015. There was a signal detected at LIGO. It happened in LIGO Leavesden 6 milliseconds before it happened in Hanford. And what we now know is that that signal was produced by a binary black hole system consisting of one black hole that is 36 times the mass of the sun and one that is 29 times the mass of the sun, and the final black hole at a mass of 62 times the mass of the sun. The signal came from somewhere in the universe about 1.3 billion light years away. So the event actually happened 1.3 billion years ago, and then in the meantime, the gravitational wave have traveled from that place to our detector. Here's the plot of the signal that was detected. You have the typical part where the black holes spiral in at a fairly low frequency and a fairly low amplitude, but as they spiral in, the frequency goes up, the amplitude goes up, and then the merger happens over here. So you might have noticed that 36 plus 29 is not actually equals 62. So there's 3 solar masses missing. And what happened to those? Those got converted into gravitational waves. Those were emitted as gravitational waves. And that amount of energy is about five times the total energy produced in a supernova. And the duration of the event was less than 0.2 seconds of the event that we observed. And that means that the total luminosity, which is the measure of energy emitted per unit time, can be estimated to be about 500 billion times the total visible light output from the Milky Way. And this is sort of numbers that are calculated by just taking the average, but the luminosity was really focused in the merger phase, and so the peak luminosity was actually even higher than that. And so this is what I really want to say. This is really magic, because this is where what I would call really magic, that the binary black hole merger essentially converts 3 solar masses into pure energy. But also it does it in such a way that you actually can get information about what the system was that actually produced it. So I mentioned that this was detected at LIGO, so I just have to say that, that LIGO has 2 detectors, one in Hanford and one in Livingston, here in Louisiana. And LIGO measures the differences in arm lengths, so it's an L-shaped detector, so one arm here, one arm going out in this direction. And by using laser light, it can measure how the length of these arms changes as a gravitational wave passes through it. It's really an impressive piece of machinery. It's even with an arm length of 4 kilometers, it still has to measure changes in distance that is of the order of 1,000 times the diameter of an atomic nucleus. And so it's a really high precision instrument that is just really amazing. If you haven't been out there to see it, I really encourage you to go. It's really an amazing place. And so far we have found 5 confirmed detections of gravitational waves, and we have found 1 signal from a binary neutron star system. So, but in order to understand these systems, it's really important to be able to do computer simulations so we can understand what we can learn from the signals. And so I'm going to show you here a movie made by some of my collaborators in Caltech and Cornell. And so what you will see here is the 2 black holes sitting here. There's kind of a sheet here that when we zoom in, I think you can go ahead and start the movie. You can see the black holes are orbiting. We are zooming in. This sheet here, you can see there's a little hole in it. That indicates essentially how strong the gravitational field are in those locations. So the time up here is the time before merger. Down here you can see the gravitational wave that is being produced by this system. And you can see slowly that the orbit is shrinking. And once we get close to the merger, the movie will slow down. And then you will see that there's very dynamic distortions in the space-time itself. You can see now we slow down, and suddenly you can see lots of peaks and stuff going on in the space-time here. And here we now have formed a common horizon. The 2 black holes have merged into 1 black hole. And then very quickly after that, it rings down and settles down to a stationary rotating black hole. And now we zoom back out again, and then out here you can see the gravitational waves signal that has been produced that has then been propagating to Earth for 1.3 billion years before we detected them. So, final slide here. Oh, I have to point in. Oh, it doesn't want to change anymore. Oh, here we go. And so the first detection of gravitational waves was what I would claim the first direct evidence that black holes exist. I don't think there's anybody who can come up with a way of producing a gravitational wave signals that looks like the one we observed without invoking black holes. And so for me, this is the real evidence. And so with that, we've now entered the era of gravitational wave astronomy. We can now use gravitational waves to learn about objects in the universe. So this is really, really amazing, because every time we open a new window to the universe, we also always find new things that we didn't expect. We haven't seen anything unexpected yet, but I think we will, because gravitational wave detectors will improve in time. Actually, LIGO is currently being upgraded to be more sensitive next time it comes online. And also we will have space-based gravitational wave detectors like LISA that will launch around 2030 that will observe completely different kind of black holes. It will observe at a different frequency and will be able to observe supermassive black holes. And so there will be many more signals to come. So this is really fascinating times where we can actually use the magic of black holes to learn about galaxies and the universe as a whole. And thank you.
Thank you so much, Peter. We only have time for a couple of questions, but if you guys have any, now's a good time. Yes? Make sure you repeat the question.
So the neutron star merger required greater sensitivity on the part of the LIGO?
Well, no, it was actually detected by LIGO being about sensitive as it was for the black holes. So the black hole signal that we saw here was very heavy objects. So the gravitational waves were at a frequency that was just coming into the LIGO sensitivity band at from about 30 hertz to about a couple of hundred hertz. While neutron stars are much smaller, so the gravitational waves coming from them will have a much higher frequency, but they will also have many more cycles in LIGO's sensitivity band. And so, because you have many more cycles, even though the amplitude of the gravitational waves are smaller, you can still dig out the signal using something called match template filtering. So, for example, the black hole merger lasted less than 0.2 seconds. The binary neutron star in-spiral that we saw lasted more than a minute. So, because you have more cycles, you can still detect them, even though the amplitude is smaller.
So, as the sensitivity of the device increases, what will it be?
So the question is, as LIGO gets more sensitive, that means that we can actually see further out in the universe. So we will be able to detect many more systems or signals. So, for example, if you improve the sensitivity of LIGO by a factor of 2, you can actually see 2 times further out, and that means you are seeing an 8 times bigger volume. And so, in principle, by improving the sensitivity of factor 2, you increase the detection rate of systems by a factor of 8. And also, if you have a nearby signal, you will really see that really, really strongly. So the question is whether the strength of gravitational waves decay as it propagates, and yes, it does. The amplitude goes down as 1 over the distance it has traveled, but only 1 over the distance, which is good. So if you observe the same object 2 times further away, the gravitational waves will be half the amplitude compared to. Yeah. So let me just repeat. So you have a table with stuff right there, and then it's the third Saturday of every month. They have an open day at LIGO where everybody can come out, and they have a really nice visitor center with lots of wave experiments and other kinds you can play around with for a long time. I see one over there.
This is the last question.
Sorry, I had a hard time hearing that. Can you speak up? So I'm not sure I understood. So the question is something related to if you're moving really fast and. Yeah, I would, yeah. So I would say, yeah. So the question was whether you could see things that happen in the future if you travel really fast. No, you can't. Anything that you observe coming towards you will have to be emitted in the past, yeah.
All right. And since I have MC privileges, I'm going to ask the first question. And that is, what on earth made you guys want to do astronomy?
What we wanted to do? Why?
Yeah.
Oh, I have a good story. So my mom took an intro astronomy class when she was doing her associate's degree in college, and she used to take me outside and show me the stars every night. So that's why I like astronomy.
I suppose I always wanted a star named after me.
Well, you have it now. Do you feel content? Fulfilled?
Satisfied, yes. Now I can do something else.
It's actually a kind of funny story. So I did my undergrad in Wyoming, and I had taken a class at my community college. I was like, yeah, astronomy is kind of cool. And it got to the point where we needed to declare majors. So I'm going through the list, and as it happens, astronomy and astrophysics is near the top. So I committed, and I stuck with it ever since.
For me, it started back when I was about 10, 11. I found a popular book on astronomy on my parents' bookshelf, and I started reading that, and then I started going to the library, and I was hooked. So, Adrian?
So, one thing I don't understand is how can they tell the distance while also telling the mass of the mergers that they're seeing with LIGO? Because to me, you would be able to say one or the other, but it's not to you can tell both.
So now I'm not actually a... Yeah, so the question is, how can you tell both the distance and the mass at the same time? I'm actually not involved in the data analysis. So okay, they're gone. I'm not exactly sure. Yeah, I would have to pass on that one for now. I would have to look up on data analysis in order to figure that out. But yeah, go to LIGO on Saturday.
Gabby didn't tell me that yet.
It's Gabby's fault.
So when the two black holes collided, some of the mass was converted into gravitational wave energy. Under what conditions does that happen?
So the question is, under what conditions does a binary black hole merger convert mass into?
Under what conditions does mass turn into gravitational wave energy? So that's one example. What would be another example?
Okay, what would be another example of doing that? Yeah, so essentially, in the binary Newton star merger, the fact that you actually see gravitational waves does mean that some of the mass of the system has been converted into energy. For Newton star merger, it's a much smaller amount than the binary black hole system. So it is also a little bit of cheating because in Einstein's general theory of relativity, energy is also mass, and so when I say that the mass was converted, it's actually sort of the potential energy of the system that has been converted into gravitational wave energy. So the fact is that you put matter into two black holes that are far apart, and so when they get closer, some potential energy gets released. And that is essentially what is getting emitted as gravitational waves.
I'm just kind of curious. There are two star-ish people here. Are you both, all four of you do stars? Or is anybody planetary?
Are there any planetary people here?
Well, we know that Peter does gravitational or general relativity stuff. Tabby and I, we do stars. We observe and measure the diameters of them, and of course Tabby's known for her own star. But Shania, what do you do? I was going to ask you for an introduction.
Oh, well. Hi, I'm a new graduate student here at LSU, and I'm working with Gabby at LIGO. Yeah. But any other questions?
So the question was, if gravitational waves can escape from the binary black hole system, can you use that to look into inside the black hole? And so the thing is that the gravitational waves that we see are actually produced by the warping of space-time around the black hole. They're not coming from inside the black hole. There are parts of the waves that are being generated that actually falls into the black hole and adds to the mass of the final black hole. But everything that we see was produced outside of the individual event horizons before they merged.
For your respective fields that you're doing research in, what is the trend, maybe this year specifically, or that you project that's going to affect things for you?
What's a trend?
Yeah.
Well, LIGO's currently being upgraded, so I guess we're expecting to see more mergers in the next observation phase, which I believe starts in February, and it's supposed to be a year long.
I'd say for the stellar galactic and maybe even extragalactic astronomy, it would be the Gaia mission, which is an European Space Agency mission that was launched several years ago, and it just put out the second data release, I believe, and providing positions and distances to like millions of stars to much precise values that we had ever even dreamed of. And this is just really opening up a whole lot of astronomy in ways that we could have never thought of before. Getting 3D maps of the galaxy and how things are moving and such like that, and it's just going to get better after that. And so that's, I think, what's going to be really transformative for us stellar and galactic astronomers moving on.
I'm actually going to have to go something a little bit narrower. So we really like our exoplanets, planets orbiting other stars. So we have the TESS mission, which just came online and is going to be giving us lots of nice data. Take Kepler, taking us from like knowing a handful of planets to knowing several thousand. It's going to be that all over again, except all over space and just absolutely incredible. So when we're looking to find habitable planets outside of the solar system, we're going to really depend on the results from TESS to point us at some great candidates.
For me personally, of course, I'm looking forward to LIGO seeing more systems and hopefully also seeing something we didn't expect to see. But personally for me, since my research right now is more tailored or targeted towards the kind of objects that LISA will see, is when LISA will fly and detect gravitational waves from supermassive black holes and something called extreme mass ratio spirals, where you have a small compact object in orbit around a supermassive black hole. That is what I'm looking forward to right now. Are we running out of questions here? Oh, there's one over there. I would say that it's speculation. So one of my colleagues, Miguel Alcubierre, so he was asking about warp drive, why I thought it was not fiction but speculation. And one of my colleagues, Miguel Alcubierre, actually wrote down a metric, a solution to the Einstein equations that essentially what it does is it contracts space near your ship and then expands again out backwards. So even when you're moving slower than the speed of light, you actually in external space can actually travel further. The problem with that space-time is that it requires, as far as I remember, strange matter with negative energy density. But we don't know if that is possible or not. I would say that is speculation at this point. I don't know. I haven't heard of it. He was asking if anybody has tried to model it.
I got a technical question. On the simulation that you showed, okay, I'm going to try something like this. So the plane, the sheet that was shown was the R-theta plane. Was it shipped down from the original?
That was a visualization. So he was asking about the plane that was below the orbit of the black hole. It was just,
Which parameter did you use to detect of the plane? Which one was the metric?
I'm not exact. I wasn't involved in making the movie. I could imagine that they were using either the labs or something called the labs that we use in numerical. It's essentially when you slice a space-time to do numerical simulation, you can let time go at different rates and different time places in your domain, and this is controlled by something called the lapse. And typically in a simulation, when the lapse is small, that's because there's a black hole. But it could also be a measure of curvature, one of the measure of a curvature invariant that they use for that. I'm not exactly sure what they use, but something that illustrates how much the curve time is warped there.
What is your favorite piece of equipment that you use in your research that you might want to use?
I don't know yet. I need more time. I just started there this past summer, and I was doing a lot of writing code to check the accelerometers at LIGO that measure the noise in the detector. So that was fun. But I don't know what my favorite piece of equipment is yet.
Okay, so I think these things called IFUs, which is a really bad acronym, they started to not use it anymore. And I can't remember the new name they gave it. So I still call it IFU. And what that stands for is an integral field spectrograph. And that's just like taking a data cube. So you're taking data in lots of different dimensions all at once and saving it all at once. And I just think that's really cool. And it had a really cool name, but it has some kind of name that nobody can remember anymore. So there you go.
So it's not something I actually use in my research, but there are telescopes constructed out of a pool of mercury that is then rotated rapidly to form the proper shape so that it reflects light and can be formed into an image. And I think that's like just the most badass way to make a telescope possible, while simultaneously being the most poisonous way to make a telescope. So if I could use that, that'd be really cool. The big downside with them, obviously, is they can only point up. But that's still pretty cool.
So I guess my favorite piece of equipment right now is my laptop where I do my code development. And once I'm done with the code development, it will probably be a supercomputer where I run my code to get some results.